this video we're going to differentiate two power functions, and the first one here is our basic quadratic f of x equals x squared. And we, of course, for the time being are using first principles, and we were introduced to first principles in the last video, and this of course is our f prime of x. The limit should look familiar as h goes to 0 of our difference quotient, and remember the fundamental difference is that now we have an expression in terms of x. So we now will get a function derived from our basic quadratic that's able to give us the tangent slope anywhere. And of course it's still based on the idea of secant slopes being transformed into tangent slopes through the limit as h approaches 0. So let's get going, and we'll set up our limit. Now when we're differentiating using the first principles definition, we typically work within the confines of the limit. We don't set up our secant slope first and then tangent slope. You just do what you did before inside the limit. And what we did before was establish what f of x plus h is, and that of course is inputting x plus h into our quadratic function. So we have to square x plus h, and then following our formula for subtracting f of x, of course, is going to subtract x squared. And that's setting up our rise in our difference quotient, and our run in our difference quotient, of course, is just h. So next step, of course, is to expand the x plus h squared in the numerator. So that'll give us x squared plus 2 hx plus h squared subtract x squared. And that's still all over h. And what happened is what we want to happen. Our x squares will cancel, x squared minus x squared, and we are left with 3 terms, 2 in the numerator, of course, and everything has an h in it. And that still leaves us with indeterminate form if h goes to 0, but at least we see a way out, because all we got to do is factor the h out of the top and cancel off the h on the bottom. We're almost done of our derivative of the basic quadratic. So h comes out of the top, and we're going to be left with 2x plus h. And then that's still all over h. So now we can divide those h's, and our indeterminate form is gone. So now we can take the limit. As h approaches 0, it's going to be 2x plus 0, and then we realize there's not much point in writing that anymore. If you want to include that step, it's a good conceptual step, but of course if you know that h goes to 0, it's probably not too shocking that 2x plus h goes to 2x. So anything with an h in it disappears at that point, and there's our derivative. And the derivative gives us a little bit of insight that we probably didn't have before. When you're looking for tangent slopes for a basic quadratic function, all you have to do is double your input, which is pretty darn elegant as opposed to struggling with secant slopes and limits and whatnot. Okay, in our second of 2 examples here in this video, we're going to differentiate the next degree power function x cubed using first principles. So the derivative via first principles is very similar to what we just did, except now we have a function that cubes its input as opposed to squaring its input. And by the way, a power function is just x to some power. Ideally, that's an integer. Positive integer is kind of what we're focusing on right now, and we'll expand that a little bit later, broaden our horizons a little bit later. But for now, let's worry about setting up our difference quotient. And I still got the quadratic on the brain. Of course, I need to be cubing things now. So here's my difference quotient, and of course I have to cube x plus h, and that gives us f of x plus h. Input x plus h into your cubing function, your basic cubic polynomial function, and of course subtract the original function from that expression as well. So we have to do some binomial expansion now to deal with indeterminate form and get rid of that h on the bottom, very similar to what we just did. So this one will be a little bit longer. But anyway, remember your Pascal triangle numbers if you're rusty, but we reviewed that a few videos ago. So you're using the 1, 3, 3, 1 here in the third row of Pascal's triangle, and you'll get x cubed plus 3hx squared plus 3h squared x plus h cubed, and then minus x cubed all over h. So of course, remember your powers have to add together to give you 3, but at this point, hopefully you're pretty comfortable with binomial expansion with something as straightforward as x plus h cubed. So what can we do? Well, we can get rid of our x cubes, our two terms on the top that don't have h's attached to them. And at this point, I'm going to do this one slightly different than the last one, which is essentially the same thing though, honestly. Instead of factoring an h out and canceling it from the bottom, I'm simply going to divide that h in the bottom into everything up top. And everything that all the h's on the top should drop by a power by 1 unit. So 3h x squared over h is 3x squared. And then 3h squared over x over h squared goes down to h to the power of 1. And then h cubed goes down to h squared. And now we can let h go to 0. And we'll have our derivative. So if h goes to 0 now, 3x squared is unaffected by that, and I will do this substitution here to make sure we're clear. H goes to 0, that 3hx term is going to go away, and then h squared is definitely going to go away. So of course our derivative here is 3x squared. So now we have a formula that can help us determine the tangent slope anywhere for the basic cubic polynomial function f of x equals x cubed. Now, interestingly, we'll see this in the next video. There's a very elegant, very simple shortcut to differentiating power functions, and you might actually see it already. If not, I'll keep you in suspense for another video. But there's a way we can use a shortcut to bypass this whole limit procedure or first principles procedure, and I'm sure that catches your interest for sure. Because like you, I'm getting sick of working with first principles, but it's an important foundation when you're working with the derivative, so at least you can appreciate the shortcuts that we'll start investing some time in the next video.